Hello, and welcome again to the show where, as per our tradition, you cannot see the host. Okay. Uh, I don't understand why it is doing that to me. So, hey, this is one angle. Oh dear. Oh dear, oh dear, oh dear. It is. This won't do. This won't do at all. I'm sorry about that. Let me fix my camera. Let's check if this is better now. It should be, hopefully. Uh, well, not at all. Okay, we'll play it by the ear. Well, maybe not. Um, this is quite ridiculous. Okay. Okay, so I guess today today we are going to use a different angle because for some reason my normal camera is dead. Okay, so welcome to Arabidol, the show where we start every other episode with some technical troubles. But other than that, what we do is that we are running hugely complicated distributed systems, reliable replicated databases with consensus and whatnot. And we actually managed to run such systems on a single laptop. Moreover, not only a single laptop, on a single thread. Specifically, these few last episodes, we've been looking at how Targabital's simulator works. How can we test that our distributed database works correctly without actually, renting a bunch of servers in the cloud and running some long running tests. Okay, so let me go to the screen sharing mode and let me share pictorially what that simulator is about. So the overall system is that we have a bunch of replicas, a bunch of separate machines communicating over the network. We simulate this system on a logical level. We model each replica as a state machine, which is parameterized over storage and network, the message bus. In our simulator, we substitute fake storage and fake message bus, and then we drive our composition of state machines. And by driving the composition of state machines, I mean that at every given point in time, we have a pile of events. We say, hey, there is this message in the network, and there is this disk operation, and they happen at different visualized point in time. So at any given step, we take the earliest event in this pile. We find the state machine which should dispatch this, which we should dispatch this event to, and we kind of manually drive that state machine. So last time we actually dived pretty deep into the specific scheduling code. We actually rewrote it, although I wasn't able to push that pull request to completion because I have a dozen of different pieces of work I'm working on right now at the same time and not finishing even one of them. But that's besides the point. So at this point, you should be pretty familiar with overall flow. But even if you haven't looked at the code, it should be pretty obvious that there is some kind of a heap of events which are ordered by their arriving time. So today, what I want us to focus on is actually how we inject faults into this system. So last time we kind of looked at the happy case. What do we do when we correctly deliver a message in our simulator? Today we are going to look at how hard are we trying to break the stuff. So we have two pieces to cover. We have to cover network failures and storage failures, and we'll start with network failures. Okay, let's go back to our lovely source code. And here we start with our test message bus. So this is the thing which we use for sending messages to the replicas. And you see that In the real message bus, we'll do that through IOU ring through TCP. In the fake message bus, we do that through the so-called network. And the network essentially does this through the so-called packet simulator. So in the happy case, we add a packet to the queue, and then at some point we dequeue this packet from the queue, and we deliver the packet, which calls the packet deliver function, which will call on message callback for the corresponding replica, which will end up invoking this callback, which drives our overall VSR library. Okay, so that is the header path. What is the set path? Let's see. So let's go back to let's get back to what sent message. So here we do not, okay, submitted. It was called submit, not send. Lesson, always use consistent names. So we've seen that like right now we've just wasted, I don't know, 5 seconds, 10 seconds looking for send packet function, because we call this thing send in our message bus. But well, in the packet simulator, we called it submit, and that's why we failed to immediately find it. Okay. So the first thing that we could fail, our packet simulator kind of like models, but kind of like more out of necessity than intentionally, the finite link capacity. So if you imagine two computers connected by some kind of a wire or maybe a Wi-Fi network, like, you know, there like physically can be only so many packets in flight between those two machines. Like, you cannot push more messages into the wire than, like, you know, the width. Like, you know, you need a bigger wire if you want more messages. Like, obviously joking, the physics is different, but the idea is the same, kind of like there is some fixed link capacity. So if the link is overflowing, some messages have to get dropped. And this is exactly what we see as our first fault injection. If we are trying to send a message to someone and the number of messages overflows our capacity, then we go and we drop a random message from this queue. But that actually kind of like, again, this is more out of necessity rather than by design, simply because we don't strictly use static allocation in our simulator, but we try to use static allocation as much as possible. So we also want to have finite link capacity. Okay, so then the actual bad stuff happens when we decide that the time has come to deliver packet. And here we have like expectedly named should drop function, which tells us whether we should just go and return packets. Return the packet. Okay, so let's see. How does that work? So we have a filter. So this should drop. Okay, let me take it back a little bit. So this particular should drop is specific to a link between two nodes. So when we submit in a packet, there is a path. So the path is like basically the edge between two nodes in the network. the source of the target is like replica, or like maybe client replica, but not to clients because clients do not talk directly with each other. So we look at the state associated with a specific pair of communicating nodes and ask where, like, this should get dropped. And here we see that we can filter out messages by the command of the message and also by, an arbitrary user-supplied function. I'm not actually sure that if we'll see this being used in developer, although it might get used to. But this is definitely used in our like manual tests. And like you see, like this failure mode is that they're not just severing the link between nodes completely, but we allow to selectively pass some subset of messages. Okay. Then we have some kind of like general, like generic drop, like that every packet can be dropped with some probability. So the model here is that we do explicit modeling of partitions. So like, our image there is like, there is like some cable in the Baltic Sea and then some like, I don't know, penguin in the Baltic Sea, like, just shoots through the cable, and the cable is not there and there is no connection. And that goes for some time. So what we're going to do in this situation is that we'll pick like subset of nodes in our network, and we say, okay, right now this nodes cannot communicate. But then later we'll say, okay, now you can communicate. And on top of that, even if the two nodes can communicate, we can drop a packet with some probability. Okay. Finally, there is this insidious failure mode where we can actually go and replay the packet. We just duplicate the packet and send it twice, which also can happen. For example, you could imagine this happening if like you're trying to send messages through one road and that doesn't work, and you are trying to send it through the other road. But actually, the first road also worked, and you end up receiving the same message twice. So in this case, we just clone the packet and resubmit it again, which will also add a randomized delay to this new packet. Okay. So how do we actually set up partitions? That happens in the tick. So tick models the passage of virtualized real time. Basically, tick is called every 10 virtual milliseconds. And here we have this partitioning logic and separately clogging logic. I'm not sure what is like clog, but well, we'll learn. Okay, so let's see. So okay. So basically, these are the two cases. If we have a partition, then with some probability, we try to heal this partition. If we don't have partition, then we try to create partition. So let's see. Okay, let's as usual, it's like always helpful to read the code backwards. So I think we'll going to read first this branch, then this branch, then this branch. Okay, so basically, when we should partition stuff, well, we should partition if we like toss a coin and it says that, hey, you should partition. So let's see how we are partitioning things. Well, first of all, we see what is our partition mode. We might be disabling partitioning. We might be selecting partitions at random. So if uniform, we just select some subset of nodes, and then we say, okay, so these nodes are partitioned. Then we do, okay, so here we kind of like pick a size at random. And here I think we randomly partition. Wait, what is partition? It's a Boolean array. Well, okay. So here I think we just randomly flip a coin for every node in our set. So we say, okay, you go left, you go right, and this won't be like uniform. So in size, here, like most of our partitions will be like half and half, and this like only same, I kind of like don't really understand what it's trying to do. It kind of like tries to disable the case where everyone ends in the same partition, but like why would you do that? Like it's pretty negligible for like large partitions. Well, anyway, yeah, and finally, like the final partitioning mode is that we try to isolate a single node. So we just go and like try to say it, okay, everyone goes to the left, but you node number n, you go to the right. Okay, so after this thing, we have a Boolean mask which says which side of a partition each node is on. Okay, then we do this thing. Okay, that's actually funny. So we kind of like have like two partitions, but we're actually modeling asymmetric partitions here. So it's not that we are going to cut the connection bidirectionally. We might cut the connection bidirectionally, but we also might cut only a single side, and that's why we roll this additional die here. Okay, then we iterate through our metrics and say that, hey, we enable a link only if like both nodes are actually parts of the nodes, because like here we increment okay, should I don't know this? Oh, okay. Well, right, no. So in our processes, I think we have clients and nodes, replicas. So it looks like we never tried to kill the connection between a client and the replica, which is not necessarily correct, I think, but okay. So anyway, so basically, like the key thing is here. So we enable the link between two nodes if they are at the same side of a partition, or if they are on a different side of the partitions, but but we allow asymmetric partitions, and like the specific node from is on a particular partition side. Okay, and then we say, hey, for this particular link between two nodes, we say that we either filter all messages or we filter none of the messages. And why my back button stopped working? This is not good at all. Let's do shoot partition to partition. Okay, finally, I want you to point out this kind of like partition stability thing, because this is also like interesting from the modeling perspective. So, like, you know, the way you could model partitions is that on every tick you could toss a coin, and if the coin comes heads, you do partition. And alternatively, if there is partition and the coin comes with a heads up, you drop partition. But that means that, like, you know, all your partitions will be like very short. You'll always be flipping between have partition and do not have partition. So what we do instead is that we have a certain minimal duration for a partition, which is called partition stability. So when we enable partition, we set this partition stability for like to this constant. And then on every tick, if our partition stability is greater than 0, then we just decrement it and don't try to change our partition situation. So if we are partitioned, we are partitioned. If we are not partitioned, we remain not partitioned until stability expires. So that's okay. So okay, it's not even like, it's not forward reading, it's not backwards reading, it's like all over the place because we understood this one and we understood this one. Well, let's say this one. This should be easy. So, okay, should partition is just probability, but again, it is modified by this partition stability. And then we just set our auto partition to false. Now, I think, like, why do we need auto partition as a field? Are we using it anywhere? Because it feels like we shouldn't. We should be fine with just local variable. Well, yeah, probably it's primarily just flogging to understand who is partition pro. Okay, so the only thing which is left is should cloak. So what is cloaked? Okay, so some probability to do a cloak, and then we cloak a path. Oh, okay, so partition separates subsets of the nodes, and clogging operates on the path. And so we set cloak till, but where do we? I'm reading cloaked till. Okay, is clogged. Oh yeah, right. So So if the path is cloaked, then what we actually do is that we are not dropping the messages as if they were partitioned, but we just delay the message and deliver a message later. Okay, so that kind of like gets you the model of fault injection. You might notice that here we don't actually inject any kind of like network corruption. We don't try to arbitrarily flip bits in the messages. And that is simply because at this level, we are operating at the logical level. So we always send complete messages to the replica. And the code which deals with validating checksums is simply not exercised by this fuzzer right now, which actually is something I probably am going to change like really soon. But for now, it is what it is. To get the actual like byte level, bit level corruption, we have to look at the storage. And that's exactly what we are going to do next, because I think we've covered the entire packet simulator, right? Well, let's quickly glance it top down to see whether we covered everything. But I think we did. So we have a bunch of parameters which configure the probabilities of partitions, like how do partitions, how long does it take to send a single message, blah, blah, blah. This is all very simple. We have this link struct, which says whom we should be dropping at any given point in time. Then there's a initialization, deinitialization, bunch of helper functions for working with links, clogging, partitioning, stepping, which is delivering the packets, and then ticking, which is simulating passage of time, then like the code to actually do the submit and receive packet logic, and that's it. Okay, yeah, we've well, we definitely covered the entire packet simulator. Let's also do the same thing for the network, but network is mostly like, just coordinating stuff. There should be, there is liveness mode. Okay, liveness mode, I will explain later. Where is our to do? So let's say liveness mode. Okay, hey, actually, this one, the last time. So that's one. That sounds good. Okay, so liveness mode, I will explain. This is just boilerplate, boilerplate, boilerplate. Yeah. So network doesn't really do anything interesting. Although we should also well, not only we have liveness mode, we also have performance mode, which I also want to explain at some point. But okay, I think at this point we fully understand how Tagbidle simulates network. And by the way, well, actually, let's just see how like this. Let's fill the simulation. So let's kick our. Oh, you could. Haha, you could even the sounds here. So let's see. They're not doing anything. Okay, so this was a message from the client. Where are the messages? Well, okay, so you see, lines there, those are exactly packets we'll see right now. It's really cool that packet simulator really got some extra code to visualize message packets being okay, so we've won. Let's see. At some point, probably I will ask Fabio to do gameplay Tagbidle, walk and talk, and Aaron will episode. But well, let's get back to the boring code. Okay, and the next bit of boring code I want to at least start covering is the storage. So let's see, testing storage. This is the same setup. So we have like write sectors, which is a function to like, which matches the real function, the real storage, and the replica calls it to write sectors. But what this thing does is that it doesn't actually do the write, it just puts this write into that heap of asynchronous things which are ordered by the time. The actual write happens in the write sector's finish function. And here we should see a bunch of fold-in logic. Okay, well, first let's take a look at the latencies, but I mean, latency, like write latency, read latency is relatively straightforward, except that write is one letter longer, so we have to do it this way so that they're symmetric. Well, anyway. So let's see. Let's see how we actually right. Oh. Okay, it's I feel pain because last time I looked at this code, there was for me to try it, but now there is reason I need to understand it to explain it. Okay, so let's maybe for now ignore misdirects and look at the more boring faults. So first of all, let's actually see like what is the state of our test and storage. How do we model it? Well, first of all, we have this memory array. And this is actually cool. So I didn't realize that it works that way, but it does. So memory models, obviously, like the actual bytes on the storage, but it models bytes as if no faults happened. So, you know, when a fault happens, instead of writing garbage to the memory, we actually write a true thing to the memory. But then we mark those sectors in the memory as faulty in the faults array. So the actual fold-in happens on the read path all the time. You do something, and you copy pristine data from memory, and then you look in the faults array, and if the faults are set, then you make a hash of byte slice. Why this is good? This is good because you could write more powerful validation routines. If a replica ends up in some invalid state, you need to be able to distinguish whether this invalid state is because you injected too many faults, so the replica is correctly saying, hey, I cannot process anything here. Or the state is invalid simply because there is a bug in the replica. And the way you do it, you actually look at the pristine memory, which you have in this test and storage, and you infer whether the replica is right or wrong based on that. Okay, so memory is the real bytes, false is which bytes should be masked with false, and then memory return is a bit set to check which bytes are not initialized at all. Okay. So, again, ignoring misdirects. So first, we are right. As we are writing stuff, we are going to override existing faults. So the model here is that if something is faulty and then we write over this faulty data, then the data heals. So if we had some corruption, then presumably by overriding it, we clear the corruption. So the first thing we do is that we clear the stuff. But what I didn't make sufficiently clear, or maybe I just lied to you, is that, like, naively, this memory consists of bytes. So you would expect that the memory written and the false bit sets track storage on the granularity of individual bytes. But that is not the case, because in our model, we model disk, we model storage as, well, a block device. That is a device which can only give you data in larger chunks, in blocks. I think we say that the minimal granularity for access and storage is okay, actually I don't know, half a kilobyte, I think. Let's see, constant sector size. Well, actually no, 4 kilobytes. So like we model disks as something which cannot give us less than 4 kilobytes data at a time. And that's why we track memory written and the faults on the granularity of sectors. So that's why we first take our write. Then we figure out what is the range of sectors which covers this write, which is like pretty simple because we know the size of the write and we know the size of the sector for kilobytes. So we divide one by the other. That's going to be the number of sectors. And the first sector we get by computing the absolute offset. So as a reminder, our physical data file is sliced into different zones, just logically. So there is like super block, the grid, the write-ahead log. And when you write, you always do this like in the logical sense. You say, hey, I'm writing to this zone at this offset. And then you convert that to an absolute offset. So it's like really, really simple. Okay, so then we at the end we go and we actually like write the real bytes into our memory. So we don't try to corrupt memory, but we do try to mark the sector as faulty. So here we use something called storage atlas, fault atlas, which I'm not sure I want to cover at this point. So let's say that maybe we'll cover it later, but like the long and the short of it is that we cannot tolerate arbitrary many faults. If every sector of every disk is corrupted, then obviously it cannot be available. So what we actually try to do is that, if you have a cluster of 6 replicas, we try to make sure that at least one, that for each sector on disk, it is not corrupted on at least one replica. So that's why we need to have cluster-wide picture of what we can actually corrupt. That is the job of fault atlas. How it does the job, I mean, to put it shortly, it does poorly, and we actually like slowly migrating from that approach. But for now, just treat it as an abstract thing which says, hey, this is the sector that you need to fault. Okay, so we have a sector that we want to fault, and then we do like a bunch of login, because login is like, I mean, so like this is the work that this function does. Just set a single bit in the bit set, one line, and this whole thing is just for logs. Because like, when you try to debug a op-amp failure, it is super important to understand like, hey, what exactly is getting corrupted. So for example, you see if we are corrupting the headers, then we don't really know which particular header we are corrupting because we don't have access to what the header should be there. Well, actually, I mean, maybe we could actually improve it and look at the memory. But, well, we don't do this. So we print simply the range of slots which occupy this sector. So our sector is 4 kilobytes. Our header is 256 bytes. So there are, I don't know, 64 headers per sector. So corrupting a single sector corrupts 64 headers. So that's why we are actually corrupting a range, and we don't know specific sectors. Our journal is a ring buffer, so it drops around. So that's why we kind of like print only slots, print sector numbers modular the size of the journal. Okay, so but yeah, that's basically faulting right. Then so we don't actually fault it, we only mark it as faulty. The actual fault happens in read sectors finish. So the first thing we do is that we actually copy the real data from memory, because we know that the data in memory is always correct. And then we go and fold it. Okay. So first, we actually like apply the same logical fault as on write, again, like with fault probability. Then we check in which manner we can fault this sector. Like, can we corrupt it? Can we misdirect it? And again, I'm not going to talk about misdirections today. Okay, misdirected idea in Wolper, but maybe some other day. So because I don't actually like understand how we determine whether we are allowed to misdirect a particular write. But anyway, so we check if our sector is corrupt. We check if our sector is uninitialized. If the sector is corrupt, we go and flip a single bit in the sector. If the sector is uninitialized, then we go and fill our sector with random bytes, and then misdirects, which we aren't covering today, and then we like do the callback. So again, that's kind of it for fault injection. We have this logical modeling of our distributed system. So this logical modeling, where the core is a heap of ready events. And then when the time comes to exercise a particular event, we just flip a coin and we apply the fault with a particular probability. For networks, we model partitions, we model packet loss, we model packet replay. We don't model actual byte corruption, because at least in the Wolper right now, everything is at the granularity of messages. But for storage, yeah, we model things like individual byte corruption as well, and also things like misdirected writes, which we haven't covered today. Okay, so I think that is basically it. You should have an understanding about how our simulator works in general, which makes me think that I need to come up with something new for the next week. But I'll leave that to Matt platform next week. And today I think we'll just wrap it up. So please join me next week at 5 p.m. UTC live on Twitch. And as a reminder, everything is always published on YouTube. So if you missed something, if you didn't understand something and want to rewatch, then the recording is going to be on YouTube basically right after I finish it uploading later today. Goodbye.